right, welcome to Introduction to Game Development. My name is David Malin, and this is
Colton Ogden.
And this is a class that assumes only a class like CS50, which is the college's and the extension school's Introduction to Computer Science. But more generally, we just assume that you have prior programming experience in most any language and therefore have some comfort with some of the basic constructs of programming. But we assume no background in Lua or Love2D or any of the frameworks that we'll be using in the class. All of that lies ahead. So if you're like me, you probably grew up with video games of some sort. And when you maybe started programming, the programming environments were perhaps very text-based, black and white terminal window and the like. And maybe you did something graphical with a language like Scratch or Alice or beyond. Or if you're in the world of the web, you've made more graphical applications of some sort, but still pretty static. The sort of content comes on the screen, then the content changes and so forth. And it's a little less obvious, if you're a little newer to programming, how you go about creating some of those games from yesteryear with which you all grew up, where there's a lot more animation, there's a lot more asynchronicity, lots of things happening at the same time, a lot of events happening, and you all not only want to capture this interactivity, but also want to respond to events that are happening, especially if you have players elsewhere next to you or online. And so the way the course will be structured is through a narrative of these various games, many of which you might have played yourself. But over the course of the semester, we dive into the context of each of these games and look at some of the underlying principles, the constructs via which they were built up, and really use them as a point of departure for talking about those various capabilities that you might integrate into your own games. And then punctuating the semester ultimately will be a number of milestones, some in the form of smaller assignments that are meant to reinforce just some of the more recent material and sort of set you up for success with the course's deeper and more hands-on projects, because indeed the projects is where you'll build or extend some of your own games. And then the class itself will culminate at the very end of the semester with your very own final project, an opportunity to propose, to design, and implement a game that somehow or other draws upon the course's lessons, so that when you walk out of here in just a few months' time, you've not only played your fair share of games, but have actually built several of your own. So without further ado, allow me to turn things over to Colton for a look and a stroll through yesteryear's Pong.
Thanks, David. I'm very excited to begin teaching you guys this course because game development was actually what got me into programming in the first place. I remember back in 2006 or 2007 buying this book here, 3D Game Programming All-in-One, which was a look through 3D game programming, and it was a monolithic text in the context of a game engine that was popular in the late 2000s called Torque. It's not as in vogue these days, but it at the time was pretty popular, and it used a language called TorqueScript. And I remember reading through this book and seeing all this code, and I had never seen like source code at all before or had ever been introduced to programming. And frankly, I found it quite intimidating because I was looking at all this syntax that I didn't understand, and I didn't know anything about game development. I had always played games growing up and been fascinated by it. But as I started getting more comfortable with computers and I started to get more curious about it and realized that it was a major profession, I started to dive a little deeper. This was my first foray, and after spending a little bit of time away from it, after looking through the source code for TorqueScript, which was rather arcane, a lot of percent symbols and dollar signs and other weird things that I just hadn't gotten my mind around, I went back to it, started to really learn the basics of programming in other languages like Python and C, and I grew to really like programming and computer science a lot. And here's just an image of what Torque looked like at the time, which is really the sort of predecessor to Unity nowadays, although in my opinion Unity does things a lot better. It was more accessible. It uses languages that are more in vogue and popular and used by other people already in other domains. And so we'll be covering Unity at the tail end of the course, and we'll be covering predominantly 2D game development. But the topics that we'll be covering today as we get started in the context of Pong are these bullet points here. Lua, which will be the language that we're using predominantly throughout the course, which is a dynamic scripting language, very similar to Python and JavaScript. We'll be covering Love2D as our primary game framework, which is a runtime and a framework which exposes all of its methods for drawing, audio, input, etc. via Lua, so that it's very easy to write code very quickly, but get very good results. And the documentation for their framework is superb, in my opinion. Today we'll be talking about a few just basic principles as we get our feet wet with game development. Things like drawing shapes, drawing text. These are both very big aspects of Pong, which is just a very simple game based on shapes and text moving around the screen. We'll be talking about delta time and velocity, which delta time is probably arguably one of the most important variables that we keep track of in any game framework or engine, which is just the amount of time that's elapsed since the last frame of execution in our game, measured in Love2D in terms of seconds, fractions of seconds. We'll be talking about game state, because you can have a state in your game. You can be at the title screen, you can be playing, you can be in a menu. This will obviously be very important because you want different update logic and rendering logic depending on what state you're in. We'll be talking about basic object-oriented programming for those who might be unfamiliar, coming from C. It's basically a way of encapsulating our data, any of our game objects, in such a way that the variables that are relevant to them are put together along with functions that will operate on that data. So instead of having like 20 different variables for all these different objects that you have to keep track of in your code, each individual object can keep track of all its own information, like its position or anything else that's relevant to it. We'll be talking about hitboxes today, predominantly in the context of box collision, because we'll be talking about Pong, which is just paddles and a ball. Those are all rectangles, and they'll be colliding with what's called axis-aligned bounding boxes, which makes calculating whether two boxes have collided very simple, as opposed to calculating rotated hitboxes, which is a bit more complicated. And then lastly, we'll polish off with sound effects, because adding that polish layer, in my opinion, is important, and it ties it all together. It makes it feel like a more cohesive whole. So two important things that we'll need to do when we're following along with the examples, which I'll show you a link to the repo in a moment, is getting Love2D installed. It's a very simple process. The first link here is just a download link, so it's available for all major operating systems, so Linux, Mac, and Windows. And then the Getting Started link down here below will give you some tips as to how to get started actually running it on your machine. On Mac, I alias the actual runtime executable within the app that it comes with. So in my bash profile, so that I can easily just type love space dot in any directory that has a main.lua file, and I can run it anywhere very simply. And there are similar instructions located on the page for other operating systems. And this is the repo here, which has all of the source code that we'll be using today. And I've structured it in a series of 13 different sub-repos so that you can follow along, and we can build upon Pong starting from scratch, going all the way to a fully implemented game. So the first thing we'll talk about is what Lua is. We'll be using Lua for about 75% of the course. It's a very popular dynamic scripting language, Portuguese for Moon, and it was invented in the early 90s as primarily a config language and a runtime language for compiled code bases to save time on adding code to those code bases and recompiling them. A lot faster and a lot easier, especially in the context of the 90s when computers were much slower, to expose the core functionality of your application to Lua so that you can just run it dynamically and then interact with your compiled code on the fly, rather than having to recompile and wait minutes, potentially hours, just to get some new behavior. It's a language that's focused around the concept of a table. Almost everything in Lua, aside from basic variables, are tables. A table is essentially a dictionary in Python or an object in JavaScript, very similar. Intended for embedded use in larger applications, and the very nature of Lua, intended to be used in the context of these large applications, meant that it was perfect for interacting with game engines, because game engines are a perfect example of code bases that are traditionally compiled code for speed purposes, but it can be very cumbersome to have to add minor functionality and then recompile it and potentially have your whole studio take hours. So we'll be using Lua and a compiled game framework, Love2D, to allow us to rapidly develop. It's similar to JavaScript and Python, a little bit more so to JavaScript, and it's very excellent because it was initially intended as a config language and just sort of a glue layer. It's very good for storing data and code together, almost one and the same. So Love2D is a fast 2D game development framework. It's compiled in C++, and it runs very efficiently because it's so simple, despite the fact that we're running it in Lua. And has modules for basically anything you would need in the context of 2D game development. Only 2D game development officially, although some people I know are working on slight little 3D experiments, but nothing official yet. But it has graphics, keyboard input, math, basically anything you could want in the context of 2D game development. It's completely free, it's portable, you can even run it on mobile and also the web, and it's excellent for prototyping. Even if you don't necessarily want to publish a game in Love2D, it's great and easy and fast just to whip something up in Love2D and then port that over to whatever framework or engine you might be using in the real world. So before we get into looking at some actual concrete code, I think the most fundamental thing we should take a look at is what a game loop is. So a game fundamentally is just an infinite loop, like a while true or a while one. Only in this case, every iteration of that loop, we're doing a set of steps back to back over and over again. We're processing input, so we're seeing, has the user pressed a key on the keyboard? Have they touched their joystick? Have they moved the mouse, clicked the mouse? If they have, we need to feed that into our update. We need to keep track of that and then change anything in our game state that relies upon that input. So we should move our paddles, we should detect collision, we should register all of this, and then whatever has updated, we want to re-render that. We want to render it, render where it's changed so that we have we see on our screen visually that things have actually changed in our game world, and we interact with it, and we get a sense that we're using something, interacting with something dynamic. And in the context of 2D games, the most fundamental way of looking at the world is via the 2D coordinate system, which is just simply, as we learned in geometry in high school, x and y axis. In this case, it's slightly different than what we typically learn. In high school, we tend to learn that the xy origin is sort of bottom left, y positive goes up, negative goes down, positive x goes right, and negative x goes left. But in this case, we're actually starting in the top left, and then it goes y positive down, y negative up, x positive right, x negative left. And everything that we want to draw in our game needs to have an x and y coordinate to draw in order for it to be visually seen on the screen. So today's goal, we're going to start fairly low level and work our way up through examples today and in future classes. Our first game is arguably one of the simplest but also one of the most famous games of all time, Pong, which was released in 1972. And the gist of Pong is you have a paddle on the left side of the screen, a paddle on the right side of the screen. Whoever scores 10 points by getting the ball past their opponent's paddle into the edge of the screen wins. And so today in our lecture, the scope is we want to first and foremost draw shapes to the screen because that's how we get our ball and paddles rendering, and those are just simply rectangles. We want to control the 2D position of these paddles because we want them to move up and down, and we want the ball to also move. We want to detect collision between the paddles and the ball because that's how we get the ball to deflect off the paddles and to deflect off the ceiling and the floor, and also how we detect whether it's gone beyond the edges of the screen such that one player scores a point. And then we want to add sound effects for sort of a feedback and sort of put ourselves into the game a little bit more. And then scorekeeping, because ultimately the purpose of the game is to beat your opponent, so we want a way to see who's scored 10 points first. And so we're going to look through a set of examples now in the repo. If we look at Pong 0, I've set this to be called the day 0 update. It's a trend among many games to have the games release major content updates as the X update. So just to be cute, I think we'll call each individual example here the something update. And so I'm going to go into the Pong 0 repo of the directory, the GitHub repo. And if we're looking at Pong 0 here, we can see it says here the day 0 update. I've commented everything fairly heavily so that we can, if you're reading the code, you can sort of get a sense of what's going on. At line 23, we're going to start off by just declaring a window width and a window height. And these are just constant variables that will be accessible throughout the rest of our application. So I'm just setting 1280 by 720 as an arbitrary resolution. Doesn't matter too much. An important thing that we need to look at here is at line 29. We're using a function called love.load, and I'm actually going to go back to the slides here. We're going to look at a few functions, and I'm going to go over them and just sort of tell you what they do before we look at the code in too much detail. So love.load is just a function that given to us by love, love2d, and we override it. We give it behavior, we tell it what to do, and love2d is going to look at it in our main.lua file. If we're looking at Pong 0, you'll see it just has a main.lua file. Love2d expects just a main.lua file and will run the main.lua file, and you can reference any other file within the directory from that main.lua file. It's our bootstrap, effectively. We are going to override love.load with whatever we want to execute at the very beginning of our application. It's just a startup function. We could also define all that behavior outside of the function above it, but it's good practice to define it within love.load so that someone reading your code will know, okay, this is where all the startup code takes place. Love.update dt is a very important function. This function takes in a variable called dt. Love passes it in a function. You're going to override it with your own behavior, and Love is going to execute this every frame, passing it in delta time. And you can use delta time dt in that function to change your application based upon how much time has passed. dt will always be a fraction of a second, potentially more depending on how slow your computer is, but typically 1/60th of a second. And you can scale anything in your game by that amount to get even behavior across all frame rates. Love.draw is the other big function amongst between update and draw, the two arguably most important functions. Love.draw is the function that we're going to define that has all of our drawing behavior, our rendering behavior in it. And that's where we can draw our paddles, we can draw our ball, and then update is where we can change the paddle's position and so forth. Two more important functions we'll take a look at in the first example. Love.graphics.printf is the Love2D analog of printf in C. The difference being that this printf lets us actually draw physically onto the screen versus a console. We give it a text as a string and an x and a y coordinate, and optionally a width and an align. And it'll draw the text at x, y, but it'll also take into consideration the width, and it'll also take into consideration the align. The width is how much to align it, and the align is the mode of alignment. So if we say x0 with our window width, and then we say align center, it's going to go between 0 and our window width and center align it. So that'll have the effect of center aligning our text. But we can just as easily say right, and it'll right align it between those two and have the effect of rendering the text along the right edge of the screen. And then lastly, love.window.setMode takes a width and a height and some optional parameters, those parameters being things like VSync and full screen, and we'll actually set up our window and get it rendering onto the screen. And so if we go back to our source code here, at line 29, we're overriding love.load. We're passing in love.window.setMode, window width and window height, which recall we defined up above as 1280 by 720. We're passing in a table. This is the syntax for a table, these curly brackets. And the way that we define keys and values is just with an equal sign therein. So full screen gets false, resizable gets false, VSync gets true. So it's going to not be full screen. It's going to be not resizable, but it is going to be synced to our monitor's refresh rate. And that's what VSync is, short for vertical sync. And then on line 40, we're overriding love.draw. And this has the love.graphics.printf function therein. And we're saying we're passing in the string hello Pong. We're starting it at x0. We're setting it at y window height divided by 2 minus 6, because the default font size in Love2D is 12 pixels tall. So we're shifting it up by 6, so it's perfectly centered vertically in the screen. And then we're setting the alignment amount, the width, to window width, so that it's going to align it within the entire width of our window. And then we're setting it to center alignment. So it's going to be center aligned within our entire window starting at x0. And so if we go to Pong 0 and then we actually run it, it has the effect of doing this. We're just rendering in our default font, default size, hello Pong right in the middle of the screen. So not a terribly exciting example, but it is showcasing the most important functions of Love2D so that we can get started with slightly more interesting examples. So our first content update is the low res update. So we're developing Pong, and Pong is an old game. It doesn't look like the example that we just looked at, where the font is fairly high res. We want something that looks a little more retro. So what we want to do is get our resolution looking like it's from a game released in 1972. So what we're going to do is look at a few more important functions here. So Pong 1 has these functions. So love.graphics.setDefaultFilter. This function, the purpose of that is every time we have a font or an image in our application, it's going to be applied a filter by default. So it's going to, by default, a bilinear filter. So what's going to happen, the effect of that is basically whenever we magnify or downscale a texture, it's going to assume that we want it to be slightly blurred so as to not look too pixelated, which is good in certain contexts. For higher res 2D game development, that's good, but as we're going to see, that's not particularly good in the context of retro games. Retro games have a very 2D, crisp, pixelated aesthetic, and we want to preserve that. And so this lets us set a default filter. We'll see that in use shortly. Another important, very important function, which is the input phase of our game loop that we saw earlier. Love.keyPressedKey is what's going to allow us to start interacting with that aspect of our game. So love.keyPressedKey is a callback function that Love expects in main.lua. We're going to override it. It gets passed in a key, and this function gets called every time by Love2D whenever we press a key. It'll detect a key pressed, and it'll call this function. Whatever we've defined in here, it'll call it, and we can set it to take in certain keys and perform certain operations on that input, and it'll get a string. So if we say, if we press the escape key, key is going to be equal to the string escape in that function, and we have access to that. And then another important function, love.event.quit. This has just the very simple effect of quitting the application, though we can call it in the code as opposed to doing it ourselves. And so here's an example of what texture filtering looks like. Point filtering is the same as nearest neighbor filtering, which is what we're going to be using. Bilinear filtering is shown on the right, where it looks pretty blurry. That's what Love2D applies by default to both fonts and to textures. And we'll see that in an example. I can actually run it in two different styles. So if we go to Pong1 in the repo, and then we run it, we see here, hello Pong is now blown up, and we'll look at some more code actually to see as to why it's blown up. But if we go back to our code, let me pull up Pong1, go to main.lua, and then I'm going to explain this in just a second, but let me comment this out, and we'll see the difference here. You can see it looks a lot blurrier. And that's the default texture filtering taking place. It applies, like I said, not only to textures, but also to fonts. And that's not the aesthetic we want. So let's look at Pong1 in detail, starting at the top. On line 28, we're requiring a library. This is how you get a library in your Love2D application or your Love application. Just equals require and then the name of the library. Push is what we're going to be using to take our 1280 by 720 window and turn it into a virtual resolution window at 432 by 243. We can start to think of our game in terms of a more low-res feel and think about it in 432 by 243 pixels, but still render it in a window that's arbitrarily sized. In this case, we're preserving the 1280 by 720 window that we saw before. If we go to our love.load function, we see this being used on line 47. Instead of love.window.set mode, we're now using push setup screen, the push library's setup screen function, where it takes a virtual width, a virtual height, our regular window width and our window height, and then the same table as before. And this has the effect of setting up a window that's got our concrete dimensions of 1280 by 720, but a virtual resolution of 432 by 243. And so now when it renders, as we'll see shortly, it's, well, as we already did see, actually, it's magnified. It has the effect of giving us a lower resolution. And on line 58, if we look at the love.keyPressed function, we've put in there if the key equals the string escape, then love.event.quit. So now we have input handling. We've overridden love.keyPressedKey, which Love2D is going to look for in our application and then call as needed. And then we're just looking in there. If the key is escape, then love.event.quit. And if I run the application, I can now press escape on my keyboard and just quit it and not have to command quit it or click the X on a Windows application. And we've changed one more thing also in the love.draw function on line 70. We're using the push library now. We need to, it functions sort of as a state machine in that we set it to start rendering at a virtual resolution with push apply start and then push apply end. And then anything in between, and this is very similar actually to how OpenGL works. We won't go into too much detail, but this is very similar in spirit to how much of OpenGL programming works. Push apply start, push apply end. Between that, whatever we call is going to render at this virtual resolution. And so we're calling the same love.graphics.printf function, hello Pong, 0, virtual height divided by 2 minus 6, same parameters, and it has the effect of rendering everything. That's still got the old aliasing going on, the texture filtering going on. It has the effect of giving us our magnified text. So same text, same size, but now our window of rendering is much smaller. So any questions so far on how any of this works? Awesome. So we've gotten text running to the screen, but we're nowhere close to Pong yet. So the first big thing I think that's going to get us closer to in that direction is what we're going to call the rectangle update. So some important functions that we should look at. Love.graphics.new font. The default font, I believe, is Arial. We don't want Arial in our application because we want something that looks a little more retro. We want something that looks more relevant. Love.graphics.new font will basically take a path to a font file that we have in our folder, which if you're in the Pong2 folder, you'll see a font.ttf file. And a size, because every font object that we instantiate needs to have a size, because the font objects are immutable. Once constructed, they cannot be changed, so they need to be allocated on a size-by-size basis. Love.graphics.setFont will take whatever font object we've acquired from this function call, and we can set it here, and it'll set the active font in Love2D to be that font. Love is a state machine in the same sense as before, in that it'll have an active font at any one time, and whatever print functions you call will use the currently active font. And that also applies to whatever color you might want to render to the screen. If you have a font and you want to maybe render it in red, you need to set Love2D's active color to red as well. Love.graphics.clear is a function that takes an RGBA quadruple and will flush the screen in that color. It just has a simple effect of wiping the screen in that color. Useful for drawing just flat colored backgrounds. And then the last function, probably the most important function, is love.graphics.rectangle. And this is the first function that we'll see that actually ends up drawing something beyond text to the screen. It takes a mode, which can be fill or line, an X and a Y, and a width and a height, and it'll draw a rectangle in that mode, so either filled, so a filled rectangle, or a line rectangle. It'll draw it at X, Y with the width and a height that we pass in. So let's go ahead and take a look at Pong2, where we can see this actually implemented. So Pong2, we have our font.ttf in there that I've included, and then a main.lua. And by the way, I forgot to mention the last example, push, the library that we required, is also just in the same directory. And you can just do require as long as the file is there within the directory, it'll just load it. You don't have to specify .lua. It assumes when you require some string that it follows with a .lua suffix. So we're here looking at main.lua in Pong2. The rectangle update. So on line 28 through 34, it's all the same stuff. We're requiring push. We have our width and height virtually and physically. In our love.load function, we are on line 43 declaring small font to be a love.graphics.new font, giving it the path font.ttf because it's right there in the same directory at size 8. And this is going to create a font object, small font, that we can then set as the active font as needed. So if we go down to line 78 in the same directory, we see we're calling love.graphics.clear. And so we're passing it in a color. I sampled some images of Pong on Google Images and saw a background gray that I liked. So 40, 45, 52, RGB, and then 255 just means completely opaque, so no transparency, the alpha component. And then we're doing the same printf function as we did before on line 81. Below that, on line 89 down through 95, we're actually calling love.graphics.rectangle. And these are drawing the two paddles and then the ball. So note love.graphics.rectangle fill mode, because we want the paddles to be completely filled, as is the ball. We're giving it an XY of 1030 and a width height of 520. And on 992, and that'll have the effect of drawing it a little bit shifted from the top left corner, 5 pixels wide, 20 pixels tall. On line 92, we're doing the same thing, except we're going virtual width minus 10. So it's going to go to the right edge of our screen, virtual width minus 10. So 432 minus 10, so 422. And then virtual height minus 50. So it's going to be slightly up from the bottom of the screen. So we have our top left paddle and our bottom right paddle. And then the ball is dead center. So we're doing another graphics rectangle call, virtual width minus 2 divided by 2. So right in the middle, minus 2, because our ball is going to be 2 pixels wide by 2 pixels tall. And same thing with virtual height minus 2, or virtual height divided by 2 minus 2. So I'm going to go ahead and cd into the Pong2 directory and run it. And that has the effect of we have our new font here in the middle, so it looks nice and retro, much more so than the Arial font as before. We have a rectangle here, 5 pixels wide by 20 pixels tall, a ball in the middle, which is 4 pixels wide by 4 pixels tall, and then a paddle in the bottom right, which is same dimensions as the paddle on the left. So it looks very similar to Pong. It's not interactive at all, but we're sort of getting the feel of what we want our application to look like. We have it mostly sketched out. So any questions so far on as to how this works? Okay, awesome. So Pong 3. So currently we have no interactivity with our application, and we want to be able to move the paddles around. We don't want to just be looking at an image the whole time. So the paddle update is going to solve this problem for us. We're going to actually get our first sort of beyond pressing escape to quit the application, we're going to get a sense of interacting with it dynamically. So the important function that we're going to look at in this example is love.keyboard.isDown some key. And this is a Boolean function. It just returns true or false depending on whether the key that we pass in as a string is currently pressed down on this frame. So it just returns true or false. And so let's go ahead and take a look at the demo. We're going to go ahead and pull up Pong 3, the main.lua therein. Notice at line 37, if you're looking in Pong 3, we have a new constant we've defined called paddle speed, which gets the value 200. And this is just an arbitrary value that I found was a good speed, but this is how fast our paddle is going to move. We're going to scale it by delta time, so we're going to multiply it by how many seconds have passed, typically a fraction of a second since the last frame, and this is going to therefore move the same distance over time, depending on whether your computer is running at 10 frames per second or 60 frames per second. So if we go down here to line 63, I've also set up two new variables, player 1 score and player 2 score. Those are both initialized at 0. We're going to add in this example also some rendering of the score. And notice here on line 49, I've also added a new font, which showcases how you need to separate fonts based on their size because they're immutable objects. Score font gets love.graphics.newFont, same exact font file, but it's 32 pixels large because the font or the score when rendered in Pong is pretty large in the middle of the screen. And so we have two different fonts now, one for rendering our message, one for rendering our score. And it's just going to render these two variables, player 1 score and player 2 score. And then we've also initialized our Y values for the rectangles, the paddles on the left and the right. We need to keep track of their Y position because paddles in Pong can only move up or down. So player 1y gets the same value we did before when we initialized the rectangle, when we drew it onto the screen. It's going to start at y30, so pretty high up. And player 2y is going to start pretty low, virtual height minus 50, which is 432 minus 50. And so in love.update, which is our first actual use of the update function on line 75, with the dt parameter that gets passed in. Remember that love2d will pass that in for us, but we need to define the behavior inside of it. We're using love.keyboard.isDown, and we're passing in the string w and s for this first block. This first block here is player 1's movement. So traditionally on computer, WASD is to move. In this example, we're going to allow ourselves to move both paddles. So we're going to use W and S for the left paddle and up or down for the right paddle. So if love.keyboard.isDown W, which means are we currently pressing the W key, player 1Y is going to get itself plus negative paddle speed times delta time. So it's going to move up. It's going to take negative paddle speed, multiply it by delta time, and add that onto our Y value, which will have the effect of shifting our paddle up. And it's the opposite for on line 82 for if we're pressing the S key. We need to increase the Y by positive paddle speed because recall, Y-axis movement is up is negative, down is positive. We're doing the exact same thing with the paddle on the right, except we're using up and down as the strings into love.keyboard.isDown. And then down below here, we are rendering, in addition to what we rendered before, also the score now. So on line 125, note that we're calling love.graphics.setFont score font, because if we don't call this, it'll use just whatever the last font was, which by default is the 8-pixel font, because we set that up top in our program. We want to set it to the score font, and then we want to call love.graphics.print. In this case, I'm just printing them in concrete places, not using printf. Virtual width divided by 2 minus 50. So no matter how we scale our window, it's always going to be 50 pixels to the left of the center of the window, and the 30 pixels to the right of the center of the window if we're rendering the player 2 score. And so if we go into Pong 3 and we run it, it looks the same as before. Note we do have score now in the middle of the screen, 0 and 0. But more importantly, we can move our paddles up and down. But there's one problem, and that's I can move beyond the edge of the screen, which is not behavior that we want in our application. So we have some interactivity. It's moving along, but we still have a long ways to go, unfortunately, or fortunately. So let's go ahead and look at the ball update. So we have paddles. They can move beyond the edge of the screen, but we don't have a ball that it just sits in the middle of the screen, and that's not what we're looking for. We want to have a ball that we can actually bounce between the paddles so we can get an actual game going beyond just moving paddles. So a few important functions we're going to look at. We're going to first look here at random. So in games, random number generation is a very common thing so that we get unpredictability and variability between different instances of our game. An important function that just belongs to Lua, it's not a Love2D thing, it's just a Lua thing, math.randomSeed num. So many of you probably heard of like a seed, like a random number generator's seed, and that just means a random number generator, because it's pseudo-random, it needs some sort of starting value to base all of its random numbers off of. It takes a starting number, it performs some mathematical operation on that number to derive new random values that we can then use in our game engine. But if we give it the same number every single time, it's just going to give us the same random numbers every single time, which means it's not going to be random at all. It's going to be very consistent. So we need a way to seed our random number generator, give it a different initial value or seed, and we're going to do that with the function math.randomSeed sumNum. os.time is an important function in the context of this because a very common way of getting a different number every time you run your application is passing it in whatever the current time is in seconds, because usually it's a very large number that is going to be different every single time you run your game no matter what, because it's based upon, in the context of most engines, in the context of Lua, the what's called Unix epoch time, which is 00 UTC January 1st, 1970, which is some huge number, 9 or 10 digits long, that changes every single second. And then in order to actually take advantage of all this, we need a function to get a random number, and so we do that with math.random, which takes a min and a max, although you don't need to technically pass a min. It'll just implicitly use min as 1 if you don't pass it a min. And it'll return a value inclusively within that range. So if we say math.random 1, 50, it'll give us a random inclusively between 1 and 50. And if we just say math.random 50, it'll do the same exact thing. It'll assume our min is 1 and give us a value between 1 and 50. And then two important mathematical functions that are very basic but helpful in the context of games almost everywhere is just math.min, which returns the lesser of two values, and math.max, which returns the greater of two values. And we'll see this in the context of clamping values to some range. So let's go ahead and take a look at a demo here. So I'm going to go ahead and open up Pong 4. And we're going to look at main.lua therein. So here on line 47, we see we're calling the math.randomSeed function as before. And note that we're passing in os.time, another function call, because os.time is going to be different every time we run our application. So we're seeding our application every time we run it based on whatever the current second is relative to 000000 January 1st, 1970, which is going to be different every single time we run, assuming we don't run it within the same second. And then if we go down to line 67 and 68, we now have, we're giving a starting value to our ball because we want to actually start manipulating our ball. So we give it an x and a y. So we're setting it right to the center again, but now we're defining a variable for it instead of just rendering it statically with our love.graphics.rectangle function, because we want this to change over time. We want to start letting our ball move around the screen. So these x and y variables are going to start changing now, and they're going to change relative to its current velocity. And its velocity is going to be stored in ball dx and ball dy. Dx and dy are common shorthands for delta x and delta y, which is how you represent velocity. So what we're going to do effectively is take whatever our delta x and delta y are and add them onto our ball frame by frame. And that's going to have the effect of updating our ball's position by some value and separating the delta x and the delta y will allow us to have different angles, different trajectories for our ball. And then another thing that we're also doing in this application, we're starting the concept of a game state, because now we can have a starting state, and what we're going to have is a play state. And so all we're going to do here in this example and this application is store our state as a string. In future examples, we're going to use what's called a state machine and actually separate out different states into their own modules. But in the context of this game, we're just going to use a simple string just to illustrate how it works. And we're going to say our first state when we start the game should be the start string, the start state. And so here on line 86, what we're going to do is solve a problem that we had in the last example, which was the paddles could move beyond the edges of the screen, which is not behavior that we should permit. So we're going to call math.max on 0 and the same operation we were doing before, and that'll have the effect of returning whichever of those two values is greater. So if the value is, if we're adding negative paddle speed to our YA value and it goes into the negative range, which means it's beyond the top edge of the screen, 0 is going to be the greater of those values, and so it'll always be 0 in that case. Math.max returns the greater of the two values. So it'll have the effect of clamping it such that it never goes above the top edge. The inverse is true for line 96, where we call math.min on virtual height minus 20 and player1.y plus paddle speed times delta time. And so this will have the same effect. It will return whichever of these two values is lesser, in which case if we've gone above virtual height minus 20, which is down at the bottom of the screen, shifted by the size of our paddle, it's going to set it to virtual height minus 20, so we never go below that point. And we're doing the same thing for player 2, exact same logic. And then if we're in the play state, we're going to actually update our ball's position. So if we're in the start state, ball's not going to move at all. But if we're in the play state, we want ball x to equal ball x plus ball x times delta time. And note that there is no shorthand in Lua for adding value to itself, which is why we're calling ball x equals ball x plus ball x times delta time instead of just saying ball x plus equals ball x times delta time. Just a language decision that they've made. But if we're in the play state, this will have the effect of scaling whatever our current ball's velocity is and times delta time, so it stays frame rate independent, and then adding it to ball x and ball y, which will shift it. And we get this actually working down here in line 174, where now instead of just rendering flat numbers to the screen, we're actually using ball x and ball y to render. And if we're in the play state, those will get updated. But if we go back up to line 127, now we're in the love.keyPressed function, so we're starting at line 120. Before, we just had the if key equals escape, then love.event.quit. But now on line 127, we're going to check to see if the key is equal to enter or return, and then we're going to use that as our way of just testing state changes. So we're going to say if the game state is equal to the start, once you press entered, game state should be equal to play. Otherwise, set it back to start. And when we set it back to start, we're going to reinitialize our x and y to be in the center, virtual width divided by 2 minus 2, virtual height divided by 2 minus 2, and we're going to give it an initial random starting velocity again. And note here, this math.random2 is equal to 1 and 100 or negative 100 is just Lua's way of doing a ternary operation. So in C, you will often have like, you would be something like math.random2 equals 1, and you would have a question mark 100 colon negative 100. It's the same exact thing, but Lua doesn't have that sort of shorthand for a ternary operation, so we do it with and or. We use logical operations instead to do the same thing. And note here, we're also showcasing that math.random can take either one argument or two arguments. In this case, we're saying math.random2, which means it'll give us a value between 1 and 2, so a 50-50. And then if we do negative 50, 50, that means we'll get a value between negative 50 and 50, so a range of 100 effectively. And so what that has the effect of doing, if we run our application, we go into Pong 4. We're in the start state, so now we're rendering. If we're in the start state, it's set to render that message. If we press enter, the ball gets a random velocity. It's actually applying the velocity frame by frame. It's updating in the update method. And if we press enter again, it gets reset, and we're back in the start state. So we do it again, it's getting a random value. Do it again, random value, random value. So every time, we're getting a different random ball value. But what happens if we try to actually run it? Or try to interact with it? Nothing. Goes straight through. So we're missing a key piece. Even though we have the core components of our game engine implemented, we don't have any concrete gameplay. Nothing's interacting. And that's a major piece that we need to look at. And so the next, before we actually start doing that, though, we're going to take a look at the class update, Pong5. And so in order to get into more of in order to scale our code more effectively, we need to start looking in terms of classes. And instead of having an x and a y for our ball, an x and a y for our paddle, a delta x, delta y for our ball, all these different variables that are sort of all over the place starting to bloat our code, before we get too crazy with it, we should think about how can we put this data all together so that we can just think in terms of our paddles or our ball object. And so we use what's called a class. If unfamiliar, a class is simply a way of taking all these variables that we've been using thus far, but putting them together in a container such that we can just say paddle.x or paddle, in this case, car. If we have a function called drive car, now we can just say car.drive instead. We don't have to have functions that are separate from our values. We can put them all together. We can ask what's our car's current mileage instead of having all these different variables all over the place. So classes are effectively blueprints. You define a class. You say, okay, my car class, it's going to have a mileage variable. It's going to have a paint variable. It's going to have a make and a model. It's going to have all these things, and it's going to maintain its own state. It's going to maintain all of that for us. As seen here. And typically, these are what are called fields. And then we'll have methods as well, functions that instead of being completely separate from this data, a car now basically owns its own functions. It has its own method called drive or turn or honk, etc. And we don't need to have a function called turn car or honk car, etc. And then this class is effectively a blueprint. We'll see shortly how to define a class. But in order to actually have one paddle that has its own set of data and another paddle that has its own set of data, we need to instantiate, create objects from this class, basically use this class as a blueprint, but take it to a factory and create concrete cars from the blueprint. And those are objects. And so, as seen here, our paddles and ball are perfect simple use cases for doing this. So let's go ahead and take a look at Pong 5. I'm going to go ahead here. So in Pong 5, immediately, if you look at the directory structure, you can see that we've added a ball.lua and a paddle.lua. And it's tradition in most languages that have object-oriented programming, as it's called, to capitalize class names, just so you can differentiate classes, for example, from concrete objects or variables or functions. So if we go to our main.lua, on line 35, we're requiring a library called class, which is what's going to allow us to actually create these classes, because classes are not a native. They are, in a sense, a native Lua feature, but Lua's way of doing object-oriented programming is a little bit convoluted. Some folks have kindly put together a library that makes it a lot simpler and a lot more closely related to other languages that do object-oriented programming more predominantly, like Java or C# or even Python. Allow us to use the keyword class in a way that's very similar to those libraries. On line 39 and 43, we're requiring our own code, paddle, and ball, and we're going to take a look at those right now so we can see what a class looks like. So I'm going to go ahead and open up the ball file, ball.lua. And we can see here all we need to do just to create a ball class is using our class library, ball gets class, and then curly brackets like that. And so now we have a class object, a class table, effectively, because everything in Lua is a table. But we can think about it in terms of objects. We have a class object called ball, And then we can start to define functions that belong to this class. So we're going to define what's called a constructor, or an init function in this case, an initializer. It's going to allow us to initialize our ball with whatever we want. In this case, we want to start our ball off with an x and a y and a width and a height. And notice within here we have a word called self. Self and this are common words in object-oriented programming languages that mean whatever object we're creating with this class is going to be self. So we'll see that we'll see that shortly. Self.x gets x. So whatever concrete object we create using this call, this init call, set its x to this x, set its y to the y, set its width, set its height. That specific object, self. And then we're doing the same thing for delta y and delta x, only that we are setting those to random values just as we did before. Self.dy, self.dx, that belongs to whatever specific object gets instantiated using this init call, as we'll see in the code. We're defining just a reset function here just to make it easy. Before we had several lines of code that set our ball to the middle of the screen and gave it a random velocity. We're doing that now, and this is a good way of sort of refactoring out groups of logic. We're creating a function called reset that just does that all in one function call, and we just call that within our main function, condensing our code. And then notice we have an update and a render function now, and we're going to call these from our own update and our own draw function, such that every object that we want in our game, every entity, and we'll build upon this game by game in the future, we'll just call update and render on everything from our main.lua and defer all of that to each individual class and objects, so we don't have to have a main.lua that's like 800 lines of code. We just break out all of the updates that are pertinent to the ball here and all the render code that's pertinent to the ball here, call each individual ball's update and render, and save ourselves a lot of time in refactoring. We're doing the same thing if we look at paddle. Paddle is a class as well. We're using the class library. Same exact sort of thing here, x, y, width, height, and a dy. In this case, we're just initializing that to 0 so that we're not moving. And then we're calling the update function here. So if our dy is less than 0, we're using the math.max function as before with the top edge of the screen, and then whatever our y plus our current dy is, so delta y. And then here, self.y gets math.min, virtual height minus self.height, self.y plus self.dy times delta time. So that's the clamping behavior that we saw before with the paddles, only now we took it from main and we put it in our update function. So each paddle calls its update, and we take some lines of code out of our main file. And then it has its own render function here, same as the paddle. The render function for the paddle and the render function for the ball are effectively the same. And so if we go to our main, we're requiring the paddle and we're requiring ball so that we can use them. So if we go down to line 79, instead of initializing our ball dx or ball dy, ball x, ball y, paddle y, player 1y, player 2y, now we have player 1 is simply paddle, 10, 30, 5, 20. And player 2 is a paddle, virtual width minus 10, virtual height minus 30, 5, 20. Ball is a ball, virtual width divided by 2 minus 2, virtual height minus 2 minus 2, divided by 2 minus 2, 4, and 4. So those paddles now have control over their own x and y, their own width and height, and the ball has its own control over the x, y, width, and height. And the self applies to this object. This is whatever self was in our constructor that we saw before. So now we can simply say player1.x, player1.width, player1.y, and everything is contained. We don't need a million variables to keep track of all the things going on in our game. And this is going to be especially important as we scale and maybe we have 100 things on the screen at one time. We don't want 100 times x variables where x is however many properties that thing has that we need to keep track of. It's all the same logic, except now we're calling player 1 update and player 2 update in our update function instead of having all that logic therein where they're moving and then keeping track of whether or not they're going past the top and bottom edges of the screen. And then if game state is play, we're now just calling ball update. And these are all getting passed in delta time. And then same thing here. Instead of having all that logic for resetting the ball as one block of code, we took it out, we refactored it, we put it into our ball class, and now all we have to do is just one line of code, ball reset. And then here, down at line 169 in our draw function, we just have player 1 render, player 2 render, ball render. And later on, as we scale and we make games that have a lot more things on the screen, a lot more entities, we can just do these renders in a loop. We can just say, for each entity in our screen, just render it. For each entity in our screen, just update it. We can condense thousands, hundreds of lines of code into just a few lines of code by deferring update logic and rendering logic to each individual entity, thanks to object-oriented programming. And so that's how we're going to refactor using classes. So any questions on how any of that works so far? Cool. This is a good point, I think, to take a 5-minute break. And then once we come back, we'll talk about how to look at frames per second. All right. So we're going to take a minute just to look at something kind of small. But often it's the case where in games, if we want to make sure that we are performing, like our application is performing well, we want some way to monitor our frames per second. And so I figured I would just take a second to illustrate this quickly so that we can use this in the future. The two functions that are going to be important for us here, well, the first of these is just a little small cosmetic addition to the application. It's just love.window.setTitle. So far, our application, I'm not entirely sure what it says by default. I think it says, what does it say? Untitled, yeah. So that's not, it's a layer of lack of polish, more or less. And it'd be nice just to solve that problem quickly. So we're going to call a function called love.window.setTitle, some string, which will solve that problem quickly. We can make it look as if we have that detailed down. And then the thing that's actually going to let us determine whether or not we are running well or running very poorly is a function called love.timer.getFramesPersecond.getFPS, which is something that Love graciously gives us for free and allows us to very easily slap it wherever we want. We can print it to the console, or we can just draw it straight to our application. In this case, we're going to do the latter. So I'm going to go ahead and go into Pong 6. In our main, if we go ahead and look at line, line 64, love.window.setTitle Pong, just quick and easy. Now our window header is set appropriately. And if we go down to line 198, here I've decided to sort of split out this in a separate function called display FPS on line 198. And the function is defined on line 207, so function display FPS. Takes no parameters. Its only goal is to just draw our current FPS to the screen. So we're going to set our current font to small font. We're going to set our color. So this is what I alluded to before, in that we can set Love's rendering color to some RGBA quadruple. And anything that we draw beyond that point will then be drawn at, whatever that color is. So in this case, we're giving it red of 0, 255 on the green, 0 blue, 255 fully opaque, which has the effect of setting our color to just completely green. And then love.graphics.print, our current FPS, we're going to string. And then our current FPS here, which is love.timer.getFPS, but it's going to return that as a number. And by default, Lua does not allow you to concatenate strings and numbers. So we're going to concatenate here with this dot operator, which is the way of doing string concatenation in Lua. We're going to call the toString function. So we're going to take in love.timer.getFPS, we're going to make it a string, and then we're going to concatenate it here. And then we're going to call love.graphics.print on that value, and then we're going to put it at 1010. So shifted just a little bit from the top left edge of the screen. So that's going to have the effect of, if we go to Pong 6 and we run it, we can see now it starts at 0 and 52 because it has to gather a few frames of data before it has a number we can actually use. But we see there FPS at 60, and so our game runs otherwise just the same. So completely random, a little bit broken, but that's OK. We'll fix it up. But currently we have a problem, and that's that our ball is just going straight through our paddles. So how can we fix this problem? We need some way of detecting collision. So in 2D games generally, there's a concept of AABB collision detection. And what this is axis-aligned bounding box collision detection, which means that we have bounding boxes, just rectangles, quads, which have an x and a y and a width and a height, which are non-rotated. So they're completely aligned with our axes. They're completely parallel and perpendicular. So the only way that we can get this easy math, the AABB collision detection working, is if we have no rotation of our boxes. They have to be completely aligned. But if they are, we have a very simple algorithm, which is we're just making sure that no edges of our boxes are outside the opposite edges of the other rectangle. So if we have one rectangle, and I'll illustrate this on the screen here. We have two rectangles. If this top edge is below this edge, we know no matter what, they're not intersecting. There's no way it can, because it's below here. So no matter where it is on the x and the y, if it's below here, it's not a collision. If this edge is on this side of this rectangle, we know as well there's no way those two boxes can overlap. And it applies to every edge as long as it is the opposite edge. So if this edge is below this one, if this edge is above this one, if this edge is on the right and this edge is on the left, it means that no matter what, those boxes aren't colliding. So we can simply do 4 conditions. We can say if rect1.x is not greater than rect2.x plus rect2.width, and rect1.x plus rect1.width is not less than rect2.x. So if the two edges are not beyond their opposite edges. Same thing with the y and the y plus rect1.height. We know that we have a collision. We know that because we haven't fulfilled any of those criteria. But we know that if that's not true, if one of the edges is not beyond the opposite edge, then we do have a collision. So it is going to be true. So we'll see that here in our code. If we go to Pong 7, at line 113, we have a function that we're calling called ball collides. Our ball class has a function called collides. So let's go ahead and take a look at our ball class. And in this case, we've defined our function such that it takes in a paddle parameter. So it's going to compare against another rectangle that has an x, y, and a width and a height. And we're saying that if Rx is greater than the paddle x plus the paddle width, which means if Rx is greater than the right edge, so if our top left is greater than or just our left is greater than the right edge, we know that we can't collide. Same thing if it's greater than the other rectangle's self.x plus self.width. In that case, if the paddle's x is basically the same operation, but from the paddle's perspective. If the paddle is greater than the rectangle on the right side, if it's farther along the right side, past the right edge, we know that there can be no collision. It's just impossible. Same thing with y. If the y, self.y, so this ball's y, is greater than the paddle's y plus the paddle height, so if it's below the edge of the paddle, because we're taking the height into consideration, or if the paddle's y is greater than this ball's y plus self.height, then we know that that also can't be a collision. But if that's not true, then we need to return true. And so if we go back to our main, oh, that's the wrong main. If we go back to main.lua here, we're calling ball.collide. So if we're in our game state, if we're in our play state, if game state is equal to play, if the ball collides with player 1, so player 1 is the left paddle, so if there's a collision detected, the ball.dx, and dx is our x velocity, so it's whatever direction it's moving on the x-axis. So it's going to be moving to the left if we detected a collision. And it doesn't matter whether it's moving left or right, but what we need to do is set it to its negative value. Because if it's moving left, and we said, let's say it's moving left at it's negative 20 pixels, and we set to 20, the dx is now 20, it's going to start moving to the right. It's going to have the effect of inverting its x velocity and therefore reversing its direction. But what we're also doing here with times 1.03 is we're multiplying a little bit just to speed up the game, because we don't want the game to into perpetuity just have the same velocity. It's not gonna ramp up the excitement. We want to keep things going. We want to get some momentum going. So what we're going to do is call ball.dx equals its negative value times a scalar that we've determined arbitrarily. In this case, I've decided it should be 1.03, so it'll increase it by 3% every time. And then in the event that we have our ball, because it's getting added, its x velocity is getting added each frame to its position, we want to make sure that it's not like inside of our paddle, because it's possible that it could shift a certain number of pixels to the left or to the right, because the same operation applies, such that the two are sort of like on top of each other. We want to shift it. We want to reset it. So what we're going to do, because it'll detect another collision immediately if that's the case. If on the next frame it's within that paddle, it's going to say that it's still colliding with that paddle, so it's going to shift its velocity again. And that's going to have the effect of it infinitely sort of bouncing back and forth within the paddle. We don't want that to happen. So if we detect a collision, we want to shift it. We want to make sure it's completely outside of the paddle's collision box. So we're saying ball.x gets player1.x plus 5 because that's the width of the paddle. So that has the effect of just, once we've detected a collision, set its x velocity to negative, and then instantly shift it right on the right edge of the left paddle. And we're doing the same thing here. If ball collides with player 2, we're inverting its x velocity. And then this is the same exact operation, but since it's based on the top left corner, we can't minus it by 5. That wouldn't make sense. We're going to minus it by 4 because that's the width of the ball. So if we minused it by 5, we would have 1 pixel of space. We plussed it by 5 on this example because we're coming in from the right side. We want to just make sure that it's right on the right edge of the paddle, so we're setting it to player1.x. And in this case, we're using the minus 4 because that's the width of the ball. So we want to shift it to the left, the width of the ball, and that'll have the effect of the right paddle. If there's a collision, it'll just get shifted over, and the ball will be touching the paddle right on their two edges. Here on line 118, we're solving the problem we had before of what happens when the oh, sorry, that's actually not what I was thinking of. This is the if there's a collision, then we want the ball's y velocity to randomize every time. So this has the effect of when we're playing the game and we've detected a collision between the two paddles, we don't want the same angle back and forth every time, because then the game will just infinitely take place the exact same, the same angles will just keep happening over and over again. We don't want that to happen. We want some variability in terms of how the ball bounces off the paddle. So what this does is, still within the condition, if the ball collides with player 1, we're going to say if the y velocity of the ball is negative, then we want to keep it going negative. We still want the ball, like if the ball's coming at a sort of an upward angle and it bounces off the paddle, we want the x velocity to shift. We want it to go the opposite direction, but we want the ball to keep going up. We don't want the ball to like bounce back down, which wouldn't make any sense. We don't want to negate the y velocity. So we're going to keep the y velocity negative. We're going to set it to a negative value between 10 and 150. And it's just arbitrary. You can set that to whatever you want. And then we're going to do the same thing if the y velocity is positive. We want the ball to we want the ball to go in the positive direction if it's already coming down. So we're doing the exact same thing here. It's the same logic in the player 2 instance. And then this was what I thought I was looking at before for a second, but this is how we fix the issue of the upper and lower boundary of the screen, right? Because it's one thing to solve the fact that we have the paddles now deflecting the ball, but we don't want the ball to infinitely go above the top edge of the screen or the bottom edge of the screen. So this is just a simple if condition. We're just saying if the ball is less than or equal to 0, which means if the ball is at the top edge of the screen, just set it to 0, so make sure it doesn't go above the edge of the screen, and then negate its y velocity. So it's instantly going to start going downwards. Yes?
This question is about Pong 7, line 113. Couldn't the shifting of the balls dx and y be done in the ball collides function if there is a collision?
The shifting of the ball's function. If ball collide, no, collides, the collides function is it just returns true or false. So it would be, I mean, I think you probably could refactor it out that way, but the purpose of collides isn't to have any sort of side effects like that. Its only purpose is just to return true or false, because we could have any sort of behavior we want in a collides function. We may not necessarily want to shift the ball or do anything. We might just want to return true and print something to the console. So in terms of, I think in an engineering perspective, it makes more sense just to have a simple true or false function and then determine how you want that to actually influence your game state inside your main function or inside some other function. Okay. And so yeah, we went down here, the top edge of the screen, and then bottom edge of the screen. If the ball.y, it's the same exact thing, just the bottom edge of the screen. If the ball.y is greater than or equal to virtual height minus 4, and we're doing virtual height minus 4, why? Exactly. So we want to make sure that right as soon as the bottom edge of the ball touches the bottom of the screen, we want to detect a collision. Then we want to say ball.y gets virtual height minus 4 in case it overshot the bottom edge based on how much time has elapsed and how much the velocity is. We want to instantly put it right up so that it's at the edge, so that it's a clean bounce. And then we want to negate the y velocity just the same as we did up above. And so if we run our program here, Pong 7, looks the same, but now the ball's bouncing. And note that it got a random, it looks like it's going below the bottom edge because my monitor is currently at 720 and that's the window resolution, but it is bouncing off the bottom edge as well. And the angle, if you note, is a little bit different every time because we are giving it a random y velocity, then that's influencing, I messed up. I wanted to illustrate the speed increase. It's going to take a little bit of time, but every time it detects a collision, it is going to be scaling the x velocity by 1.03. So it's going to make it a little bit faster. Now currently the y angle is a bit steep, so it's going to take forever to illustrate that, but we'll see that in a later example. So we have the basics of our game, but how are we keeping score? What's the determining factor for how we keep score in Pong? Left or right, as long as it goes past the left or right edge of the screen. So what do we need to thereby do? We do need a counter, and we need to also monitor whether the ball has collided with the left or the right boundary of the screen, and then have that increment that counter. So we're going to go ahead and take a look at Pong 8 to see how this is implemented. We have here on line 88 and 89 some counter variables, player 1 score, player 2 score. We've had those for a long time, but we haven't used them. We've only used them to draw to the screen. We're actually going to now increment them and show them as scorekeeping variables in our code here. I thought I had implemented it in Pong 8, but I think I might have left out the actual incrementing of the score. But this is the logic that's pertinent to that example. So if ball.x is less than 0, which just means if we've gone past the left edge of the screen, ignore serving player for now. The important thing is now we are doing player 2 score gets player 2 score plus 1, just a simple increment, and then we're resetting the ball. Same thing for here. If the ball.x is greater than virtual width, so past the right edge of the screen, and it actually could be if ball x plus 4 is greater than virtual width, then and it will have the same effect. But actually, no, because we want to make sure that we don't see the ball at all when they score. So yeah, this is actually correct. If ball.x is greater than virtual width, then serving player gets 2. Player 1 score is player 1 score plus 1, and then we're going to reset the ball. Serving player. So now what we need to talk about is the idea of serving. So when we start up the game, so let's go ahead and take a look at we're going to go to Pong 9. So we're going to go straight through Pong 9, and then we need to take a look at what a state machine is. So currently in the game, we've talked about state a little bit. We've had the start state, which means the game is ready for us to just press enter, and then the ball will go off in a random direction. And then we have the play state, and the play state is set to our paddles interacting with the ball and then keeping track of score, basically. A state machine is very important. It's a ubiquitous concept in game development. It just means how can we monitor what state we're in and what transitions take place between those states to bring out new states. And each individual state has its own logic. And by breaking out the logic of these states separately, we can scale our code much bigger and not have monolithic code. This particular diagram is an example of what you might have as a state machine for a character like Mario, where you have a ducking state, a release state, which takes the input of down. So if releasing down, he'll become standing. So ducking state, the transition is release the down key, he becomes standing. Standing key, press the down key, he becomes ducking. These are states and transitions. These individual states are the overall representation of his behavior at large, basically. And the same logic applies to our game. We have a play state, we have a serve state. We want to have maybe a game over state. If someone scores 10 points, then it should say, oh, the winner is X. And you can define any arbitrary number of states that which depends upon your model, whatever game you want to develop. For example, like Super Mario has a title screen. Maybe your game has like a high score state. You want to display all the high scores in your game, and we'll actually show that in a lecture next week. But this is what a state machine is. It's just it can be in any one particular state at one time, and the transitions are what allow you to go in between your states. And each state does have transitions in and out of other states. And we're going to use this in Pong 9. So beyond illustrating the score, we're going to start keeping track of more than just the start and the play state. We're actually going to start modeling the serve state. And so let me go ahead and illustrate what this looks like. So if we're here, I just pressed enter. We started at the start state as normal, but I pressed enter, and now it says player 1 serve. So we're actually serving. And so if I press enter again, as it instructs me, player 1's on the left, the ball should move to the right, which it does. So I'm going to go ahead and lose on purpose as player 2, and now it's player 2's serve. So whichever player loses should get to serve again. And so now if I press enter, note when we were player 1, the ball moved to the right. So if we're player 2, the ball moves to the left. So we have now a little bit more interaction. We have different states. We start off the game, and then we serve, and we play. So when the ball's live, when we're actually doing this, we're in the play state. Now we're in the serve state. So what's the transition between the play state and the serve state? What's the transition there? We score a point. So if we're looking at our state diagram and we're in the play state, the transition to the serve state is X player scores a point. And then if we're in the serve state, the transition is someone presses enter. Enter key gets pressed. And so that's how we want to think about our games. If we have a bunch of different sets of sort of logic that we can sort of take out of our game and think about conceptually, it allows us to break our game up into a bunch of different modes and states and not really get overburdened by all these variables that maybe need to keep track of, or what state are we in, like what are all these variables doing? And we'll see how we can break this out in a more modular fashion in future weeks. Note that right now, currently all we're doing is we're setting a state variable to some string here and just doing if conditions on it, which works fantastically for small examples. So if, like, for example, if we're in the update function and game state, see here we're just saying if the game state is set to serve, then we're initializing all of the variables. If the game state is play, then we need to actually perform our logic here. So if we're in play, this is going to get called each frame, and we're going to say if ball collides with player 1, do all this stuff, and then this allows us to sort of think of our game. It's almost like having separate update functions within our update function. And we'll actually see how we can take these out of one update function in future weeks with a actual state machine class and implement things a little bit more abstractly. But suffice to say, now whenever we want to, like, for example, make a transition, if someone scores here, like if we're going to the left side of the screen, if ball.x is less than 0, all we have to do is just set this state to serve, and our update function is then going to update appropriately. So any questions on how sort of state machines or the state works here in the context of Pong? Yes?
So the state machine is the relationship between the states, or is it the container of the states?
The state machine is sort of the overall conceptual look at what your different states are and their transitions, yes. And in future weeks, we're not implementing a state machine object or a class here, but in future weeks, we will see a state machine class that manages transitions between different states in a more modular and clean fashion. All we're doing here is our state machine is just if statements and saying if the state is equal to this, then do this, and then change the state to some value.
So the state machine is like a concept?
It is a concept, yeah. But we will see an implementation of a state machine as an object next week. So, any more questions? Okay, cool. So, currently we have scoring. As we saw, the player 1 score and player 2 score are getting incremented now, and those therefore getting rendered to the screen whenever we go to the left or the right edge. So we're keeping track of score, but what do we need now in order for someone to win? Sorry? Yes, it does. Exactly. So it's actually quite simple. All we need to really do is just an if statement, right? If someone's score is equal to some value, 10, then some player has won. So if we look at Pong 10, we go to main, and go to here, line 174, and also line 160, we can see that all it literally is in our logic from before, where we're just testing to see whether the ball has gone beyond the left or the right edge, because this is effectively where you need to do your check anyway to see whether someone scored a point. So all we're doing is adding logic to that part of the program and saying, after we increment their score, if it's equal to 10, we're setting a value called winning player. We're going to set it to 2. So if the ball.x is less than 0, then that means that player 1 got scored on because it went past the left edge of the screen. Therefore, player 2 score should go up, and therefore the winning player should be 2 if the player 2 score is equal to 10. And in this case, see, we're setting a new state, done. And then if that's not the case, so if their score is still less than 10, we should set it back to serve and then reset the ball. And so if we go to our update function, here actually we're doing it in our update phase. So currently, if it's the done state, the ball gets reset, but no update is being applied to the ball in that case. We still have scores 10. It'll still render the scores, so score whoever's got 10, and it'll show the other player's score. And the actual logic that applies here, whenever we want to break out of that state, is in our love.keyPressed key function. We see here on line 227, if game state is equal to done, which we set it to before, and this will only execute if they've pressed enter or return, so it's effectively waiting for them to press enter or return. We want to set game state back to serve. We want to reset the ball. We want to initialize their scores back to 0, so we're setting up a brand new game effectively. If the winning player is 1, then we'll give serving player to 2 so that they have the advantage on the next game, and then otherwise set it to 1. And if we go down to our render function, so down to line 275, if we're in the done state, then we should render to the screen player and then winning player, because remember we set winning player to 1 or 2 depending on who won, depending on who scored the 10th point. We'll say player 1 or 2 wins, and we'll just render that, and then press enter to restart after that, and that's the logic for that. And we can see this and play. Also, if it's too slow, we might not have to go through an entire run. But I sped up the whoops, don't want to actually hit the ball back. I set up the speed, so we're in the serve state, we're in the play state. It's up, the ball bounced back. It's going to be a bit tedious, but suffice to say, it's a big payoff. Don't worry. Should have set the speed a little faster. Almost there. It's getting tense. And player 1 wins. So there we're also setting the font to a larger size. And in the code, I create a new font object that's basically between the small font and the score font, which is a large font, so 16 size font. And so player 1 wins. And that's really all it boils down to, just keeping track of your counter and just making sure that when you do hit 10 in your logic for detecting the screen collisions, that you set the state to done. And if the state is done, then you just need to monitor keyboard input and see whenever someone presses enter. So when we press enter in our love.keyPressed, it has the effect of setting it's player 2 serve because player 1 won, so it's only fair. We're going to press enter to serve, and then we begin a brand new game. And that's simple. So now we have an infinitely playable game with a bunch of simple states. We're missing a very important detail, though, in my opinion, and that's sound. Currently, our game is just very... It's great. The gameplay all works. Everything's working fine, but it's just missing a little polish. And so what we're going to do is we're going to start adding audio to the game, which is, in my opinion, one of the more fun things to add because it also means you're close to the end of your project. Love.audio.newSource is a function we're going to look at here. All this is going to do is take a path and then optionally a type. And this path is going to be to a sound file. And it's going to create an audio object that you can play back at any point in your application. So what we're going to effectively do is just whenever a collision happens, depending on what type of collision it is, we'll just play a particular sound. And a program that I really like to use for all of this, what I encourage you guys to download if you want to start tinkering with your own sounds for your project, is a program called BFXer. It's free on Windows and Mac. I'm not sure if they have a Linux port. They might have a Linux port of a similar program called SFXer, which is what this is based off of. But what this allows you to do is just generate a bunch of random sounds, and I can illustrate that shortly for you. If you would like to grab it, it's on bfxer.net. It's a super quick download, and here I'll demonstrate it just so we can see how it plays out. So this is the interface. Make sure I have some audio, and then there's a lot of different presets here. So there's pickup / coin. Laser / shoot. It's meant for sort of like small games like this, like implementing on the fly prototype audio type stuff. But you can see it just implements. I'll turn that down, it's a little loud. We have power ups, for example. So every time I click on this, it's going to give us a random power up. So. And then randomized, you get all sorts of weird, nasty stuff. And then the stuff that we'll use is blip / select. Most of the things in our interfaces and games like Pong, you just want simple sounds like this. So I've already done the work of generating a few sounds that I thought fit pretty well. I'll go ahead and show you the code first in Pong 11. If you look in the directory structure, you'll see we have a sounds folder. In the sounds folder, I've created 3 sounds. Paddle hit, which is anytime the paddle hits the ball. Score, which is when anytime the ball goes past the left or the right boundary of the screen. And then wall hit, so anytime the ball touches the top or the bottom of the screen. And so the logic of this is extremely simple. All we need to do is whenever, we already have it implemented, so all we need to do is, first thing I should say, and this is a good illustration of a table. We'll start to see this a lot more in the future. We didn't really use tables much in this lecture, but the table is Lua's like sort of be-all, end-all data structure. It's the dictionary, Python dictionary, JavaScript object. It's an array. It's everything that you need for anything beyond simple variables in Lua. It's what everything, even like classes and other libraries, are made out of. In this case, we're just initializing a table here called sounds. And we're passing in 3 keys, so it can take in key value pairs, or you can just give it a list of values, and it'll create indices for them implicitly. Here we're just passing in, like you would do in Python or JavaScript, paddle hit. And note that it does need these square brackets in order to initialize key value pairs in a table like in this format here. Paddle hit gets love.audio.newSource, and in this case it just takes in a path, so sound/paddlehit.wave, and we're giving it the keyword or the string static, which is the type of asset it is it's stored as. So you can have either static or stream audio assets. So if they're static, they're loaded in memory and they're kept in memory for the execution of your program. If they're stream, then they're loaded on the fly as needed by your game engine. And streamed audio assets can be helpful if you have a huge game with a ton of sounds and large audio files. You don't want to keep all those in memory necessarily, because that could take up many megs or gigs of audio. And if you're sort of loading assets on the fly, if you have dynamic loading in your game, then that's another thing you should take into consideration. In this case, these are very tiny sound files because they're like a fraction of a second long. So we're just setting them all to static so that they get preserved in memory, and we're just loading all three of them into this table. And if we want to refer to these later on, all we need to do is sounds. We can either reference sounds dot paddle hit like that if we wanted to, because by default Lua just gives you a dot keyword, sort of the way JavaScript does its objects, with the same name as the key that you passed in. Or you can do it the Pythonic way, which is without the dot, with just square brackets, and that will have the same. Those two are equivalent. It won't work though if you decide to put a space in your key. It will, I believe, it just won't work at all, but it may inject an underscore. I'll have to test it out and find out. But generally, it's not best practice to use dot when you already have the keys lined up like this anyway. And what you can do with strings that you can't do with dot, using the dot notation, is dynamically generate a lookup of your table, which you can do with strings, because you can't in a for loop do for something in table and then table dot something. That just won't work. But you can do for everything in your table and then look up the key as that value, that iterated value in your table. And we'll see examples of that in future lectures, but just something to keep in mind. So we have our table here, a sounds table, and we have our sounds ready. They're loaded in memory. All we need to do now is wherever we have anything that, like any collision in our code, we just do this. It's as simple as the table at the key that we want, colon, which is Lua's way of calling a function of a class or a table, colon play, and the play function is part of the new source audio object in Love that we created in the table, and that'll just have the effect of just playing it once. You can set it to looping. You can say the sounds paddle hit set looping to true, and it'll just infinitely play it over and over again, which we wouldn't want for a sound like this. It would sound obnoxious. But if you have a music track, for example, in a level or something like that, you would want set looping to be true, so that when it finally ends, your user isn't just playing a game in silence. So we're doing it with paddle hit. We're doing it with wall hit as well. So I've named them appropriately so that it's easy to infer where and for what purpose the sound files are used. So whenever they're at the upper or lower boundaries, play the wall hit sound. And then whenever the ball reaches the left or the right edge of the screen, just play the score sound effect. And so if we play our game, and this is always one of my more favorite parts, is playing the game with audio, because it just makes such a difference in my opinion, we get sound effects. It's a little thing, and it's very easy, but it adds so much flavor. And there we go. And then our game is practically implemented at this point. There's just one more example that I would like to show you guys, a small example, because all of the examples thus far have had the resizable equals false sort of key in the push setup screen initializer. And in case you want to have a game where you can resize your window, all we need to do is call a function called love.resize, which takes a width and a height. And what we're going to end up doing with that, specifically for our use case, because we're using push, we're going to go to Pong 12. And then if we go to main.lua, we see here on line 85, I've changed resizable to equal true now, so that it'll actually allow us to resize the application. If that's false, you won't even be able to click and drag the bottom corner of the screen. It just won't let you do it. And then all you have to do is call love.resize with height, and then pass in push resize with height, because push underneath the hood takes a texture and renders to it and then upscales it to fill your window. And so it needs to know what your current window dimensions are so that it can upscale it to fit the right dimensions. And push also adds things like letterboxing, which is convenient if you want to maintain the exact same aspect ratio. And in a game where maybe you have a UI that's driven by the size of your application, this function will be important, because then you can resize and reposition your UI elements appropriately. Because if your game is small, maybe you want certain parts of your UI to be invisible or in a different location altogether, just so that you don't take up a ton of screen space, and just to accommodate all possible users of your application. But that has the effect now of, if we go into Pong 12 and then run it, actually, I might even not even be able to use the bot. Yeah, I can just do this now. I can resize it, and it'll maintain the virtual width and height that we set it to before, because that's like first and foremost what push will do, and it'll letterbox no matter what size your application is, to make sure that it maintains that aspect ratio. So if you're beyond that aspect ratio vertically or horizontally, you'll get the appropriate letterboxing for it. So it's super convenient. You don't have to worry about your users getting super distorted aspect ratios because they're using some sort of unforeseen resolution. It'll always maintain it, even if it's super tiny because their monitor is super thin. It'll always maintain the aspect ratio. But that's pretty much it for Pong, actually. We have a complete game, start to finish. And if you have any questions, I'd be happy to answer them. No? Any questions? Cool. All right, well, I'm excited to teach the rest of this course with you guys. We've only scratched the surface. We have a lot more to cover. Next week, we'll actually be covering Flappy Bird. So we'll get some nice, colorful graphics, which is a stark difference to our black and white aesthetics today. But that's it for Pong. So thanks for coming.